Hello, everyone. Once again, it's Pharmaceutical Calculations with Dr. Dave. In this lesson, we're going to be talking about non-sterile liquids. So in the previous lectures, we talked about mostly powders and how to describe concentration of powders and make powders. Now we're going to apply that same concept, but we're going to apply it to liquids. So some of it is the same, and there is a little bit of difference in terms of the measurement of concentration and how we define that. But let's start with non-sterile dosage forms. So non-sterile dosage forms, when we say that, we're referring to things that are given that are usually on the outside of the body or taken orally. So solutions and syrups that are taken orally, and emulsions, elixirs, and certain lotions that are really liquids can be applied. So usually it's stuff that we put on our skin and that we take. Now, don't get confused by the term non-sterile. There still are products that are not contaminated, but the sterile products, when we use that term sterile products, we're talking about things that are injected, inhaled, or put into the eyes and sometimes the ears. So if you're going to inject somebody with something, you want to make sure that it is non-sterile. If you put something on their skin, it's not necessarily has to be non-sterile, but the environment in which it's made is still regulated. So the concept of a liquid, when we talk about them, we really, in a sense, are boiling it down to two things. Number one is we take a solvent, right, and we put a solute into it. So we dissolve something into it. So when we dissolve something into it, right, two things can happen. That solute can dissolve, and in that case, it turns into a solution, right? Or that can turn into a suspension or emulsion if it doesn't dissolve. So that's like putting salt in water, it would dissolve, you'd get a solution. If I put sand in water, the sand would not dissolve and you would get a suspension. Or if it's an oil in water, you would get an emulsion. So two liquids mixed together. For our sake, when we're talking about dissolving solutes that do dissolve, so if you're making solutions, we're looking at whether or not that solute is an electrolyte or that solute is a non-electrolyte. And depending upon that is sometimes how we label the concentrations or talk about them. So if something is like sugar or even so sucrose or glycerin, if I put that into a liquid, they will dissolve, but they don't get charged when they're in solution. So they're non-ionic, non-electrolytes. If you have electrolytes, like I said, sodium chloride or hydrochloric acid, I'm sure you've done the pH pKa types of equations where you have the ionization of those things, you're going to have ions in solution. Those are electrolytes. We describe them differently. So let's look at how we are expressing the concentrations of liquids. When we look at a liquid, we are usually looking at the amount of that solute that is in a certain amount of volume, right, of solution, or a certain mass of that solvent or solution. So let's look at the details in particular. The first thing is the percent concentrations that we have gone through many times, and you see it again here. It's the exact same thing you saw previously, nothing new. It's just put here for completeness. If you have something that was, let's say, a 7%, right, weight in volume solution, you know that this is going to represent 7 grams of the solute in 100 mLs of the solution, right? So the full solution, right? Not the amount of solvent, the solution itself. If you do see something that says milligram percent, so if I had 7 milligram percent, in this case, this means 7 milligrams in that same 100 mLs of solution, right? If something just says 7%, right? If it says 7%, and you know that it's a powder, so if I have a 7% sucrose solution, which is sugar and water, you know that sugar would be a material you'd weigh, and it would be going into a liquid. You can assume that without anything else, that this would be weight and volume. Right? So if it's not stated, you can assume if you know something is dissolved that it's weight and volume, and it's going to be grams per 100 mLs. The other one is volume and volume. We discussed before, if I have 7% volume and volume, that's saying that there is 7 mLs per 100 mLs of the solution. Again, the full solution. So the units are mLs in both cases, in the numerator and the denominator. If you don't see anything, if I say a 7%, like we had isopropyl alcohol solution, you can assume that that means that there's 7 mLs of pure isopropyl alcohol in 100 mLs of the total solution. So let's take that concept, do a little bit of math. Okay, let's look at an example here. Let's say that you have 400 mLs of a 20% weight and volume solution, and that's going to be diluted to 2 liters, let's say. What will be the final percent strength of that? So let's look here and break this down from a pitcher standpoint. If I was to take a container, a vessel, and say a really large beaker, according to this question, it says you started with 400 mLs, right, of a 20% weight and volume solution, right? That means that there's 20 grams of material in every 100 mLs, but this is 400 mLs of that 20%. Then it says we diluted it. So we added some more of that solvent up to the 2 liters, which in our case is going to be 2,000 mLs, right? So went from 400 mLs to 2,000 mLs. And it's asking us, well, what is the final concentration here of this new, right? What's the percent concentration there? Well, the way I would approach this question is that I would start with, well, what is the amount of drug that's in this first 400 mLs, right? How much drug is in here? I know it's a 20% solution, so that means that there's 20 grams of material in every 100 mLs. I've got 400 mLs, right, of the solution. So if I know that I've got 20 grams for every 100 mLs, which is the assumption I'm going to use with 20% weight and volume, and I've got 400 of that, I'm going to say that I've got 80 grams, we're going to call this a drug, right? So we know right here in this beaker, within this 20% right here, there is 80 grams of drug right there. Now I'm going to add water to it, and just because I add water to it up to the, or whatever the solvent is, up to the 2,000 mLs, doesn't change the amount of drug. The drug stays the same, but now that same 80 grams is distributed within 2,000 mLs instead of 4,000 mLs. So to do a concentration, we're looking at amount of drug, 80 grams of drug, right? Amount of solution, 2,000 mLs. Right? In order to get a percent strength, I'm looking for the amount of drug, or amount of grams of drug per 100 mLs. Well, there's 80 grams in 2,000 mLs. How much drug is there going to be in 100 mLs? If I do that math out, I get my 80 grams is in 2,000 mLs. How much is there if I only got 100 mLs? And I've got 4, right? That's my 4. That's the number of grams, right, per 100 mLs, or 4%, right? So the final solution will be 4%. All right. Another way in which we can do a question that's like this and other questions that are similar is something that I'm going to refer to as C1V1 equals C2V2. This is a simplified form of getting the answer when you know 3 things out of 4. If you know the concentration of some liquid and the amount you have of that liquid, that means you have a concentration 1 and you have a volume of something. And you know either the concentration of another thing or the volume of another thing, you know that they will always be equal. The reason why this holds true is that this is the amount of drug or the amount of active that you're finding. And the amount of active, like we said in the picture, stays the same even though the volume is changing over here. So even though the volume is changing, the amount of active is staying the same. So this equation works. So we can solve the above question that we had by doing the same thing. If we had our C1V1, C2V2, we could have said that C1V1, right, is equal to C2V2. We could have said C1 was a concentration of something, which was 20%, right? And the volume of that was 400 mLs. And the concentration of something, number 2, is what we don't know. That's our X. And the volume that we said was 2,000 mLs. Notice you have to have the units that are the same on both sides. Doesn't really matter what they are, but the units have to be the same on both sides. So you couldn't have mLs or liters. You'd have to always have the same thing, and that equation will work. And you'll notice if you do that, X will give you the 4%. So let's do another example that we utilize this. Here's the question is saying, you've got 500 mLs of a 15% volume and volume solution, and it's diluted to 1,500 mLs. And it says, what's the percent of the dilution? How do you label the final percentage of the product that you just diluted down? You can answer this the same as like the way we just did previously, or you will notice that we've got a volume associated with a concentration, and we've got another volume, and we're looking for a concentration, right? So we've got 3 of those 4. So we can utilize the C1V1 equals C2V2. Or you can do it the previous way we did. You don't have to utilize this, right? It's just a shortened way to get your answer, but it's done the exact same way that this one up here is done. So in our case, we would say 500 mLs. Or let me do it in terms of the numbers here. So C1, which is 15%, right? V2, or C1 is 15%, V1 is 500 mLs. So it's the volume of something and the concentration of that same thing. And here we have our concentration that we're looking for, that's X. And our V2 is 1,500 mLs, meaning that's the volume that it's diluted to. This is telling you that the amount of drug on the left side is going to equal to the amount of drug or active on the right side, the amount of liquid on the right side. So this is why the equation works, as long as the units are the same. Now, you can keep the numbers as a percentage, right, and just keep them as 15, and then this number will already be a percent, or you can change this to 0.15, but notice that when you get an answer for X, you've got to multiply that by 100 to turn it into a percent. So either way you want. I like to just keep them with the percent signs there, so I know when my answer, when I solve for X, it's going to have the percent there. So that means I'm going to take 15 times 500, okay? And then I'm going to divide that by my 1,500, and I'm going to solve for X, and I get 5. So I know that X is equal to 5, right? X is equal to 5, and it's equal to 5%, because that's my unit right there. So this would be 5%. So the final amount, the percentage, will be 5%. All right. You can also use the C1V1 equals C2V2 to have other problems that, again, have that same sort of a relationship where you have a concentration and a volume and another concentration or volume that you're looking to solve for. So this one says, how many milliliters of a 2% elixir, which is a alcoholic sort of based oral liquid, that can be prepared from 45 mLs of a 3.5% elixir. All right, so keep in mind that we can use C1V1 equals C2V2, or you can do it the other way. I'll show you both ways if you'd like. If I did this with the C1V1 equals C2V2, how do I know I can use that? Because I have a concentration, and I have a volume, and I have a concentration, and I have something I'm looking for, volume, right, mLs. So let's take C1V1. Let's take the ones we know. Concentration of 1 is 3.5%. The volume of that 1 is 45 mLs, right? And this says it equals C2. Now we have a concentration 2%, right? And we're looking for a volume this time, in mLs, x mLs. So what do we get when we solve that? So this is 3.5, multiplying that by 45, and then I'm dividing it by 2. So I've got 78.75. 78.75, and x, right? X is equal to this, and this is mLs, because that's the units there. Making sure units on both sides are the same for the concentration in the liquid. All right. I could have also done it the other way. Again, the reason why this works is because I'm finding the amount of drug. The amount of drug, right, times the concentration times the volume will give me the amount of active. The concentration times the volume will give me the amount of active. The amount of active stays the same even though I'm diluting it. Right? So this was 45 mLs, and I've got 3.5% elixir. So that means that there's 3.5, right? In our case, you can say volume or grams. It doesn't really matter, but 3.5 amount of drug per every 100 mLs. And I've got 45 mLs. So the question will be, well, I've got 3.5. Do that, 3.5, and I've got that 100, and I've got 45 of that. So I've got 1.575 grams of drug, right? And it says, well, how many milliliters of a 2% solution can you make? 2% means that there's 2 grams in every 100 mLs. So I'm going to write it this way. In every 100 mLs of that elixir, right, I need 2 grams. If I've got 1.575 grams, right, how much elixir can I make? So 100, divide that by 2, and then multiply that by my 1.575, and I get that, right? 100 divided by 2 times 1.55, and then 78.75. Just did my math wrong in the calculator. So 78.75. Notice, same thing. Same answer, whatever way you want to do it, because the amount of drug is staying the same. All right, let's look at another one where we do ratio strength. So now we have the same sort of question. We're looking at liquids, we're describing the concentrations, and we have how many milliliters of a 1 to 500 weight and volume stock solution should be used in preparing 1,000 mLs of a 0.05% weight and volume solution. Again, the biggest problem that most people have is just understanding what the heck the question is asking us, right? What is this question asking us? How can we approach this? So take it step by step, right? It's asking us first, how many milliliters of this solution, right, do we need to prepare 1,000 mLs of a 0.15% weight and volume solution? So let's draw that out, right? I've got my little beaker, my container, whatever you want it to be, and this is saying that I want to prepare 1,000 mLs, right? And I want this to be 0.15% weight and volume, right? And it's saying, so how many milliliters of this stock solution do I have to add into here, right? How many milliliters of this do I have to add into there to get that concentration of drug, right? So it's asking us really, how much of this stock solution do I need to take, this concentrated stock solution do I need to take right here and put into here so that that becomes the source of my drug, right? So let's do that question out. How much drug do you need here? How much drug do you actually need if you needed to make 0.15% weight and volume and you wanted to make 1,000 mLs? That's telling me that I need 0.15 grams of drug in every 100 mLs of that I want to make. I'm going to make I want to make 1,000 mLs. If I want to make 1,000 mLs, how much drug is there here? How much drug is there? That's what I'm finding out here. Well, I know that there's 0.15 grams every time there's 100 mLs, and this time we have 1,000 mLs, so I've got 1.5 grams. So I need, this is what I need. I need 1.5 grams of drug. I've got to get 1.5 grams of drug inside of this liquid, this 1,000 mLs. How do I do that? I'm going to use this stock solution. So how much of that stock solution will give me 1.5 grams? That's what the question is really asking me. How much of this solution will give me 1.5 grams? So let's ask that question. What does the 1 to 500 weight and volume stock solution mean? Again, it means that every 1 gram is in 500 mLs of the stock solution. All right? So I'm going to write that this way. So I know that there's 500 mLs, right? 500 mLs will contain 1 gram of drug. Right? If I need 1.5 grams of the drug, right, how much mLs do I need? What's the mLs that I need? So let's figure it out. Every 500 mLs of that stock solution will contain 1 gram of drug. How many mLs will be if I want 1.5 grams? And there it is, 750 mLs. So if I take 750 mLs of this stock solution and I put it in here, and then I QS to 1,000, I would make my 0.15% weight volume solution. All right, let's look at another one where we're looking at those parts per billion, parts per million situation. This one we're talking about a parts per million. So it says a commercially available insulin preparation contains 1 ppm of proinsulin. So a very small amount of proinsulin is in this finished product. It says how many micrograms of proinsulin will there be in a 10 ml vial. So if you got insulin you're giving to a patient, there's a level of proinsulin that's in there at a very low level of 1 ppm. So if a person gets a vial, which is a 10 ml vial, how much of that proinsulin is in that entire vial? That's what the question is asking us. What does 1 ppm mean? 1 ppm means that there is 1, right, gram of proinsulin in every 1, right, million, in our case mLs, because we're dealing with a liquid. So that's 1 gram for every 1 million mLs. We could also look at that as saying that we've got ppms, which is also, we can say micrograms per ml as well. If you convert this here, grams, 1 gram is equal to this is our milligrams, and then we go 3 more, and that's our micrograms. So you'll notice that this is micrograms, right, per 1 million mLs. All those zeros cancel out, and you get a 1-to-1, which is also the same thing as saying micrograms per ml. So if there's 1 microgram per ml, and you've got 10 mLs, you know that there's going to be 10 micrograms. You can do it just most likely from your head, it's going to be 10 micrograms, but you can also do it the way in which we have here. If you know that there's 1 gram per every 1 million, right, mLs, how many, if you've got 10 mLs, and that's what you're getting, and that's where you get that 10 micrograms. Notice this is grams, I've converted it to micrograms. You're going to get a decimal there. All right. Let's move on to an example where we're doing the same thing again. Remember, so it's the same concept, it's just utilizing a liquid this time instead of utilizing powders. And one of the things we did with semi-solids, right, is that we took semi-solids and we mixed them together by the alligation methods, and we got different concentration mixtures. Well, we can do the exact same thing here. So here it's telling us how many mLs of a 35% and a 10% solution would be required to prepare 100 mLs of a 20% solution. We want to make a 20% solution, and in front of us we've got 2 bottles, right? I got 1 bottle that's 35%, and I've got another bottle that's 10%. I want to make a 20%. That's what the question's asking me. How much of each of these do I have to mix to get my 20%? And I want exactly 100 mLs, right, of a 20%. So remember the tic-tac-toe almost, the alligation? So we've got two concentrations, right? And we're looking for something else. We put the highest one on top. It says 35%, right? Lowest on the bottom, 10%. The one we want in the middle, 20%. Once we get that, we do our subtraction method, right? We take the difference, the absolute value between the difference between these two, which would be 15, and we take the difference here, which is going to be 10. This tells us the ratio, right? Remember, this is the ratio of this and this, right? That's what that tells us. And then we also can do the total here, right? Which would be 25 parts total. Sometimes we need this, sometimes we don't. Realize when you do and when you don't. So we know that we need 10 parts, right? 10 parts of the 35% and 15 parts of the 10%. Or you can say, I need 10 mLs of the 35% every time I'm going to mix that with 15 mLs of the 10% to make 25 mLs total. So if I mix 10 mLs of the 35%, 15 mLs of the 10%, I'd get 25 mLs total. And so now I can do that relationship to find out what the answer is asking us. The question rather is asking us. We want to prepare 100 mLs of a 20% solution. Right? So if I want to prepare a specific amount of solution, is saying 100 mLs, right? This tells me that I need 10 mLs, right, of, I'm going to call it the 35%, right, every time I make 25 mLs, right? But I want to make 100 mLs, right? So I know that I need 10% of that 35% concentration liquid every time I want to make 25 mLs. If I want to make 100 mLs, I'm going to need 40. So right now of this, I need 40 mLs. How much of the 10% do I need? I do the same thing. This is telling me that I need 15 mLs, right? Every time I'm going to make 25 mLs total. This is 15 mLs of the 10%. Keep in mind, I'm writing the word 10% and I'm writing the word 35%. These are not part of the math. They are a description of what I'm writing, right? So if I need 15 mLs of the 10%, every time I want to make 25 mLs, how much if I want to make 100 mLs? And you could do the math there. It's 15 mLs of the liquid every time I want to make 25 total. I want to make 100 total. What do I need? 60. And notice that 40 plus 60 will give me my 100, right? Total mLs, right? So I'm going to mix 60 mLs of this. So 60 mLs of the 10, 40 mLs of the 35%, I get 100 mLs, 20%. Same methods we did with powders, with the semi-solid mixtures, same thing we're doing with solutions. You'll know it's an alligation problem most likely because you're going to be asked to, or I shouldn't say you're going to be asked, you usually will see two percentages, right? And you're going to be asked to get a third percentage. It's typically an alligation problem. Sometimes it'll tell you how much you need total parts, which is this case is telling you how much you need total, or it will tell you have a certain amount. Like I have 100 mLs of 10%. How do I dilute it down to get to 20% in this or so, or concentrate it up to get to 20%? In that case, you use the ratio between the two. So you got to do those problems up. Just realize it. Once you realize it, it'll make more sense. We can do a few of them when you use the total parts or when you're using the relationship between the two. All right. The next section that we're going to talk about, which some people probably have already been exposed to in some of their science, chemistry sort of things, is the difference between molarity, molality, and normality. It is not a big emphasis in this course to go over these, but for the sake of understanding what they are, because they will play a little bit of a role when we look at electrolyte solutions, we're going to just go over them relatively quickly in this section. All right, so looking at molarity first. Molarity defined by the number of moles of solute in 1 liter of the solution. Keep in mind this is solution, all right, the total solution. In order to find the number of moles, it's easy to consider that if you know the molecular weight of the compound, you will know that that would be equal to the amount of moles. So for example, if I say I've got 58, or sorry, if the molecular weight of sodium chloride was 58.44, right? Assuming this is the number of grams per mole. So if I had 58.44 grams of sodium chloride on my balance, I know that that would be equivalent to 1 mole of sodium chloride. Right? And if I weighed out on my balance 82.5 grams of sodium chloride, well, if I know that 1 mole is equal to 58.44 grams, I can tell you how many moles there are in 82.5 grams, right? And that will give me that approximately 1.47 here. So just utilizing molecular weights to get moles. I'm sure you have been aware of that in other courses. Now, because temperature does affect volume of liquids, right? A cold temperature or hot temperature can change the volume associated with a liquid. That's why when we do measure volume, it usually has a temperature associated with when that was done. We can use molality, the 2 L's, right, to determine a way in which we can describe the number of moles of solute, and this is divided by the weight of the solvent, not the solution, of the actual solvent used in kilograms, right? So it's the number of moles over weight of solvent in the mixture. So no volume is going to be in there. So let's take an example here. This says if an aqueous solution of ferrous sulfate was prepared, it added 41.5 grams of ferrous sulfate in enough water to make 1,000 mLs. What is the molarity of the final solution? So draw my lovely picture so I can have reference. I have a volume container. Inside of it, it is going to have 41.5 grams, right, of ferrous sulfate. And it's going to have a total volume of 1,000 mLs. And it says, what is the molarity of the final solution? Well, so if I want to know what the molarity is, I look at my equation. Molarity is moles over volume in liters. I'm going to call this moles over volume in liters. All right, so liters. So I need to get number of moles, and I need to get number of liters. Well, the liters is the easy part. 1,000 mLs, I can convert mLs into liters, and I know that's 1, right? Easy. All right, 1,000 mLs per liter. Number of moles, well, again, we said what's the molecular weight, and we can utilize that. So ferrous sulfate's molecular weight says 151.9. So that means that I've got 1 mole every time I weigh out 151.9 grams of the ferrous sulfate. If I'm going to only have 41.5 grams of the ferrous sulfate, which is right here, how many moles is that equal to? 1 mole is, as we said, 151.9 grams. Well, if I only have 41.5, how many moles do I have? 0.273, right? That would be my molarity of the solution. All right, so we can say 27, let's say 32. And this is the molarity of the solution. Notice big M molarity, small m molality. So I would say 0.2732 big M molarity. All right. This is a question taking into something we learned previously about density and utilizing it to solve another problem for molality. So it says if the density of the ferrous sulfate liquid prepared above, so if the density of this right here was determined to be 1.0375, what is the molality of the solution? Well, first, let's find out, what do I need if I want to know molality? Molality, right, is number of moles over the kilograms of solvent. So little m, right, little m for molarity is, I'm going to need number of moles, and I need to divide that by the kilograms of solvent, right? Now, how many moles of ferrous sulfate is in this above example? We know how many moles it is, right? It was that number. It was that 0.2732, right? This is number of moles. What I don't know is how many kilograms of solvent is in here. How much weight did I put of solvent in here, and how would I get that? Well, let's take a few things. We given density, right? We're given the density, right, as 1.0375. Right? What is the density? Right? This would be grams per ml. Right? Grams per ml. All right. Now, if we know that there's 1.0375 grams, right, in every ml, and we made 1,000 mLs, right, 1,000 mLs, I can take this and multiply it by 1,000. Right. All right. So times that by 1,000 is going to be, I think I have the wrong number, sorry, 1.0375 times the 1,000 mLs. It gives me that 10375.5 grams. What did I just determine? I determined the weight of this 1,000 mLs. So this 1,000 mLs here weighs 1,037.5 grams. That's what I just found out. That's how much that weighs. Well, I know how much it weighs. That's good. But I'm still looking for kilogram of solvent. That's what I'm trying to solve here, is for a kilogram of solvent. How do I get that number? Well, if I know that the total of volume here, right, it weighs 1,037.5 grams. I know that I put 41.5 grams of ferrous sulfate in there. So if I take this 1,037.5 and I minus, right, let me write this in blue here. If I minus the 41.5 grams, which was the ferrous sulfate, what else is left in this? There's nothing else. It's just the ferrous sulfate and the liquid. That's all that was mixed in there. So I know the remaining of that. So if I was to take 1037.5 and I minus my 41.5 from it, I get 996 grams. What is this? This is saying 996 grams. This is of the solvent, right? That's what's here in this, right? If I take 41.5 grams of ferrous sulfate and I add to that my 996 grams of the solvent, right, I'm going to get my 1,375. So the bottom denominator here is this, 996. So now taking my 0.2732 and dividing that by 996, I'm going to get that number. And you're going to say to me, oh, you forgot to do something. And you would be correct that I need this to be in kilograms, not grams. So I would have to convert this into 0.996 kilograms and get my answer that way. So 0.2732. Try this again. 0.2732. Divide this by 0.996, and now I get my number 0.274. Let's call it 2743 is the small m. All right, so that's how we get molality. So molarity, number of moles over kilograms of the solvent is the molality. The molarity is moles per liter of the solution. All right. The last one we looked at is that we'll look at is normality. Okay, the last thing about the normality that we'll just be discussing is it's really like molarity, and I'll show you at the end here how it relates, but you really need the same denominator, so you need the volume of the solution, but the number on top, you need something called the gram equivalence. And the gram equivalence can be given by this equation down here, where you're taking the molecular weight and then you're dividing by the valence, right? That's really what you're doing, and that's the number of equivalents of the solvent. So you can read through that and see how they relate, but for sake of brevity, if you take the atomic weight, right, which is here in that column, and you divide it by its valence, you get the equivalent weight that's there. So the equivalent weight is that it has a relationship between the valence. If the valence is 1, then, for example, potassium, then the atomic weight or the number of grams per mole would be the same if you got the atomic weight or you're looking at the equivalent weight. If I do an example, I think it'll give you a little bit of clarity as to how we do this. Keep in mind that if you can solve for molarity, which is the number of moles per liter, which most people can do, all you got to do is multiply by the valence and you get the normality. Right? But I'll show you both ways here in this last question here. It says, if the normality of a solution, or what is the normality of a solution by dissolving 67 grams of sulfuric acid in 5 liters of water? I'm going to show you 2 ways. I'm going to show you first the way that's here. If you take the molality of the solution, so we know the big M, right? It's number of moles divided by liters, right, of the solution, right? Well, we know that the amount of liters of solution is equal to 5, right? That's 5 liters. And we know that the molecular weight for the sulfuric acid is 98 grams per mole. So as a side calculation, if I've got 1 mole every time I have 98 grams, right? Sorry, that is 1 mole. I have 1 mole every time I have 98 grams. How many moles if I've got 67 grams, right? So that's what I can do here. 1 mole is 98. How much do I have if I've got 67? And I've got that number, 0.63. Right? That's going to be the number on top here, 0.683, what is it? 67. You can keep it in your calculator. And then I'm going to divide that by 5, and I get this number. So my molality is equal to 0.1367, right? Now that is the molarity, right, of the solution. If I multiply it by the valence in this case, it shows us 2, right? Because it dissociates. So we have the 2. If I multiply this by 2, I get that number, which is equal to, I'm going to take this number. So if I take M, right, times 2, I get 0.27, was it 35? 35. This is equal to my normality, big N, normality. So I can get normality by taking molarity and then multiplying it by valence, or I can do it by the equation that we said. The equation up here, right? If you look for the equation of normality, we're looking for number of gram equivalents per liter, right? So normality, big N, liters, right? And we're looking for the, I'll call it gram equivalent weight. The number of liters is given to us, 5 liters. Easy. What's the gram equivalent weight? We take the molecular weight, 98, and we divide it by the valence, which is 2. 98 divided by 2, we get 49. So 49, right, is the equivalent weight, is the gram equivalent weight for the sulfuric acid that we're doing about. Now, this is just like the way in which we do grams per mole here. This is saying that there's 1 gram equivalent weight every time we have 49 grams. I've got 67 grams, all right? What is the total amount that I have? Well, I've got every 1 gram equivalent weight is every time I have 49 grams. I've got 67 grams. I've got 1.3673. 1.6, what did I say? 36. So 3673, all right? That number is what's going to go on top here. If I keep that in my calculator and I divide that by 5, I'm going to get that same number I got, 2735, right down here, right? That would be the other way to do it with the equation. Most people find this one to be a little bit quicker because they're very familiar with molarity, and all you're doing is multiplying your answer by the valence. All right. So that ends the discussion on how to make now non-sterile products when we're mixing and matching them with different concentrations, how to describe concentration of them, and how to look at normality, molarity, and normality in this. All right. So as always, this is the most important class, pharmacy calculations, because it's the only one that counts.